All right, there are four types of resistors that we're going to speak about. Fixed, potentiometers, rheostats, and what I call special application resistors. All right, we're also going to talk about the resistance color code and the tolerance. All right, the resistor color code determines the ohmic value of the resistor, and the tolerance is another color we'll see I think it's maybe several slides down, that will determine the tolerance of the resistor. And you'll see when we get there what I mean by that. We'll also take a closer look at potentiometers and rheostats and adjustable resistors. And we'll end this with a definition and some theory on special application resistors, which I call thermistors and varistors. So let's go on to the next slide, and let's start this journey. Okay, on this slide here, we're looking at some physical resistors. And right here, on this side here, we have what I call my fixed resistor types, meaning that the resistance value or the ohmic value is fixed, one value, period. You can't adjust it. And if you look at these here, we have a carbon film and a metal film resistor. Okay, that's the material that the resistor is made of. Now, if you look here, you'll see that there's just 4 bands here. All right, and if you look at my metal film resistor right here, you'll see that there are 5 bands. Now, because of the material, all right, a metal film resistor has a tighter tolerance and a better temperature coefficient than my carbon film resistor. Carbon film resistors are a little bit more common, but you'll also see a lot of metal film. What do I mean by temperature coefficient? As the environment that the circuit is in, okay, as that changes, as that gets hotter or colder, the value of the resistance will change. It'll change with temperature. So when I say a metal film has a tighter temperature coefficient, the resistor value will stay closer to what I'll call the published value of the resistor here, the color code, and it will stay closer to that. Where a carbon film, it'll vary much more. Now, is that a problem? It depends upon the application and the circuit. Okay, over here we have potentiometers right there, or I should say variable resistors, which a potentiometer is one class or one form of adjustable resistors. If you look here, that is a potentiometer, and you turn that clockwise or counterclockwise, and you can turn that shaft 270 degrees. But the point I want to make here is, if you look right here, you'll see 2 sets of terminals. Each set has 3 connections. Let me clear that slide as we go on. So this shaft attaches to a double gang potentiometer. So when you turn that, the resistance of each section tracks. One of the things that they might want to do with that is if you've got a stereo and they want to track two channels, you can turn the potentiometer, and simultaneously the resistance on each track will be the same. The same thing here with this one here. All right. Over here we have a multi-turn potentiometer, where these guys here, it's 270 degrees to go from one end, or counterclockwise to clockwise, where this guy here it may be 5, 10, 15, or 20 turns to go from the very minimal resistance to my maximum resistance. And what does that do? We'll see in the next slide or two coming up that I can get a finer adjustment with a multi-turn potentiometer than I can with a standard potentiometer where the revolution or one turn is 270 degrees. Okay, let's look at another style of variable resistor called the rheostat. And in a few slides up, you'll see the difference between the potentiometer and the rheostat. Okay, but just looking at these here, looking how they physically work, this rheostat is on a slide, and you slide it back and forth, and that changes the resistance. Over here is like a screwdriver adjustment, and you turn this shaft, and that also adjusts the resistance. And here we have a shaft where we can turn the shaft and again change the resistance. So in the next slide, they're coming. I don't remember exactly which order they're in. We're going to look at the differences between the potentiometer and the rheostat here. All right, so let's go on here to varistors and thermistors, and I'm going to explain them. Varistors and thermistors are special application resistors, and again, we're going to look at them a little deeper at the very end of this presentation. But a varistor right here is a voltage-dependent resistor. So it's voltage dependent, where a thermistor right here is temperature, and I'll abbreviate temperature right there, temperature sensitive. So in a varistor, when I have a voltage across this varistor, the resistance will change, and when I'm using a thermistor, depending upon the temperature or the environment that this is in, the resistance will change. With a thermistor, we have two types. We have a positive temperature coefficient and a negative temperature coefficient. On a positive temperature coefficient, when the temperature increases, so doesn't the resistor. On a negative temperature coefficient, as temperature rises, the resistance of the thermistor goes down. The other thing I want to mention here is the material and the actual physical mounting. Notice this is a radial lead, this is an axial lead, and this is how we can mount them on the circuit board. This one is made out of glass. All right, so we'll take a look at these later down. I think when we speak about varistors and thermistors, they're at the very end of this presentation. So let's move on here. Okay, and on this slide, I show you several sizes of fixed value resistors, and they range from 3 watts down to 1/16 of a watt. Now, I'm going to define what a watt is just here. I'm going to just show you the formula. All right, when you take my circuit analysis course, we'll get into it deeper. But power of a component, which will determine the wattage rating, equals the voltage across the component, in this case the resistor, times the current flow through it. And current is abbreviated by I, so that's current. All right, so for instance, if I make a calculation here, and I say that the amount of power that's dissipated by the resistor, and I'm using specifically resistor here because that's what we're talking about, is a 1/2 watt, then the component or the or the wattage rating of the resistor that I should place inside this circuit would be a 1 watt resistor, because what we want to do is we want to overcompensate it. So if I calculate a 1/2 watt, I want to make sure that the component that I put in there, or the resistor value that I put in there, is double that or greater. And greater is okay too, but we would like to see at least 2 times the calculated value. Okay, the next thing I want to speak about is the colorings. And on these resistor pictures, you'll see that I have 4 bands, and you can count them. All right. The first digit is closest to the left. You'll notice that all these resistors, if you look at them, and I'm going to clear the slide off, but I just wanted to emphasize that, is closest to the left. That is the first digit. Okay. Now, on a 4-band resistor, and as I'm talking, I'm going to clear the slide off. On a 4, because we have 4 and 5-band resistors. All right. So on a 4-band resistor, you'll notice, and this one's very pronounced, that's gold. This is gold, 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 gold there. All right. The last band, or the band all the way to the right, is the tolerance band. Very hard to get a period with this. Okay, is the tolerance band, and I abbreviated tolerance right there. Okay, the tolerance band is the specification on the resistor. In other words, that resistor may not be exactly the published value of the resistor, which is determined in this case by the first 3 bands right there. All right. So there's a tolerance, plus or minus 5%, plus or minus 10%, plus or minus 2%. Okay, we'll see how to calculate that in upcoming slides, but that's the tolerance band. The tolerance band says, okay, I've got this value resistor. The upper limit can be as high as this, and the lower limit can be as low as that. And we'll see as we go on. All right, so now let's stop here and go on to the next slide. Okay, on this slide here, we're going to introduce the color code. And what I've done is I've given you a little bit of a poem to try to remember the colors. And the little poem, a little saying, is right here. Big boys race out young girls, but violet generally wins. Now, the first letter of this poem represents a color. And what you have to remember is that we go from a dark color, which is black, up to a bright color, which is white. All right? And the first letter of the first word in the poem is the first letter of the color. For instance, big is black. Boys is brown. All right? Big black represents 0. Boys brown represents 1. Race represents red, and it's the number 2. Hour equals orange, and that's the number 3. Young represents yellow, and that's the number 4. Girls represents green, and that's 5. Butt represents blue, and that's 6. Violet is violet, and that represents 7. And generally equals gray, and that's 8. Wins equals white, and that's 9. So again, we go from a very dark color to a very light color. If you can remember that poem, it'll make life easier for you. All right. So that's all I'm going to say here. I just take a look at this and try to remember it. And we're going to go on to the next slide. Okay, let's move on now to part 2. And in part 2, I show you how to use the resistor color code. We determine some values of resistors. I show you how to do it. And there's a couple of problems for you to do. So let's move on.